Good morning. Good morning. Welcome to Primetime. I'm Deb Sullivan, trainer from the Faculty Development Office in CAS. And this is a joint collaboration between the Friends of the Library and the BU Library that has a focus on scholarship sometimes on teaching, and sometimes on student study abroad experience. And our goal is to encourage each other in lifelong learning. And I always enjoy them because I just learn about what's going on in different departments. So I really appreciate you being here this morning. Faculty, we're here. Be sure to be on the lookout for research papers and projects. The library has a library research prize of $250. So as papers start to come in, as the end of the semester approaches, keep those in mind to nominate them for the research prize. Next Tuesday, November 8th, students will share their experience on the G92 immigration conference that they went to at Cedarville University. So that will be a student focus. Today we have a science-focused talk by Dr. Chad Hoyt in physics. And he's going to present his recent research using lasers and a magnetic field to cool and trap millions of lithium atoms at a temperature of a few hundred microkelvin. And his talk used to have it actually a funnier, a more interesting title. So he's changed it a little bit. It was originally called "The Coldest Place on Campus" by a factor of 100,000. Yeah?
Thanks, Larry. I decided to be a little bit less provocative in the title.
It worked. You got people here, so.
Yeah. It is true, and I hope to explain my title a little bit in a few minutes. Thanks to the Friends of the Library, and thanks to the library itself for this time. Is it free coffee? Great. Thanks for coming. I want to tell you a little bit about our work in the physics department, particularly in the atomic, molecular, and optical physics lab. And what I'm really going to show you is student work. So I sometimes get to talk about student work for them. The students sometimes get to talk about their own work. And recently, this year, we've had some neat opportunities to do that. Jessica Dorman, who is a senior that's doing research with me for her senior research, we just traveled to San Jose, and she presented this work at a really nice conference there. Jack Holton, who's here too, earlier this year, he and I traveled to Anaheim to present some of this work. So it's really student work, and I'm lucky enough this morning to have some coffee and be able to tell you about their work. This work couldn't be done without funding, and I list that here. The NASA Minnesota Space Grant Consortium, and some private funding from CID and funding from Bethel University, which we're very grateful for. Oh, this thing doesn't fly here. It's a big team. We've been working on this, really the lithium cooling and trapping project since 2009, 2008, 2009. But there's some early work, even back when I first came to Bethel up here in 2007. So I list here all of the students that have worked on this team, been a part of this long project, and a lot of them have graduated, which is good. And I show you here some of the places that they've gone. A lot of grad school. Here's Mathematica. Sarah was a Mathematica expert. And then down here, these are the names that I showed you on the first slide. Dan Clement, who's here. Thank you for me, Dan. Sarah Venditto, who had just finished her first year in Bethel Physics, came into the lab and worked with us last summer. And then again, Jessica Dorman. And then Jack Holton also was with us for half of the summer. Does anybody have a laser pointer that might work? And then he went off to a PhD program in Boulder, despite my best efforts to keep him here by saying his library fines were too great, or holding their account, I just couldn't keep him. So he's off to do fun things. So it's a big team, and every part is important, including the part played by these folks. I couldn't find a picture of Terry Sandquist. You might remember him, but he was a former team leader of facilities management. So Greg, you probably recognize Greg. Chuck is HVAC specialist. Jerry is a lead plumber. And Tom, of course, runs the show there. But I like to build stuff in the lab. to answer scientific questions. These guys like to build stuff too. And that's their careers, and they're a very important part of what goes on in the lab. And we have to tell you about all the stories. I thought about telling you a story about Jerry and I, the details of the story, but Jerry and I came up with a scheme to save tens of thousands of dollars in the lab with a cooling, a water cooling thing. So that was a lot of fun working with Jerry on that. Okay, so my first provocative title is Coldest Place on Campus by a factor of 100,000. So I felt like I needed to sort of justify that to you. So here it is. What I've done is shown you temperature scales. Red is in Celsius. Use my finger. Red is in Celsius, and blue is in Fahrenheit, as it says. So the way you read this is the absolute temperature scale is in Kelvin. Okay, so most scientific work is listed in Kelvin. So 0 Kelvin is absolute 0. And there are reasons why you can't actually get there. You can get pretty close. So the how you go from Kelvin to these other scales is with this graph. So this would be, for example, 0 Celsius is right here, and that corresponds to about roughly 270 Kelvin. Okay, you might already know this sort of thing. And then, of course, 0 Celsius corresponds to about 32 Fahrenheit. Okay, so you see how you read this, and it goes down from there. So I put some lines here to give us some idea of the scale here. This is room temperature. It's about 300 Kelvin in here, about 70-something Fahrenheit, and 20-something Celsius. This also illustrates why our temperature measurement is better than the Europeans, right? Because the slope of this line is much greater than the slope of this line. You get more resolution with this line than you do for this one, right? Or change it. No. Anyways, so here's, say, freezing, ice, water right in here. This is where I stop riding my bike. But sometimes I'm fooled. It's really nice and sunny outside, and I get out there, and I say, well, it's a little bit cold out here. And I get to work, and I check the temperature, and it's below 0. I think, what just happened? Can't believe I live here. So there's some familiar stuff up here. What might not be so familiar is what's happening down here. This is about, what, 70-something Kelvin, far below 0 on either scale. And this is actually the temperature of liquid nitrogen. You might know this from lots of fun. Maybe you had a demo in science class when you were a kid. You put things into liquid nitrogen and they freeze so cold that it just freezes. Like you put a rose into liquid nitrogen, you take it out, and you break it, and it comes apart. I wish I had some to illustrate this, but I don't. It's also what, for example, a doctor, thanks, what a doctor might use to burn off a wart, for example, is liquid nitrogen. Down here, this line, now we're starting to get into a lot of interesting action down here. And this is really where I'm going to spend time here, the rest of our time. But right before I get to the temperature of the cold lithium atoms is liquid helium. That gets pretty cold. It's down to the single Kelvin range. And it takes a lot of work to work with liquid helium. But we're down here, cold lithium. And you see, here is 0. So on this scale, we're pretty much at 0. So we have to talk, let's see how this goes, 0, 50, 100. We're at 0.0001. So it doesn't even coincidence with 0 here. Okay, so put another way, and I really want to, this is where I justify my provocative title. What I have here is a temperature scale. This is like a thermometer, okay, showing you different readings here. So this would be 3,000 Kelvin. So this is off the charts on the right side of what I just showed you. This is the temperature of the surface of the sun. Okay, hot. Okay. What we do is we drop it by an order of magnitude from this one to this one. This is in the 1 Kelvin scale, so this is 300 Kelvin. As I just showed you, this is the laboratory, and roughly on this scale, it's a cold day. Laboratory and cold day. So now we get to 30 Kelvin, 3 Kelvin. Remember I showed you this is where liquid helium comes in, and so forth. We get down to, and then we divide by a factor of 10, and then we jump to a whole different sort of range here. This is the millikelvin range. This is 0.001 Kelvin. All of this is happening now down to by 0. So 300 millikelvin, 33. Then we drop another one to microkelvin, 300 microkelvin, 33. And then we get into this nanokelvin business, which when you get down there, physicists often think, well, what is temperature becomes not a useful measurement anymore because there's almost no movement in it. But just the same, I show it on this scale here. So, surface of the sun is up here. We drop 1 order of magnitude. We get laboratory and cold day. I thought there might be some chemistry folks here. Once a year they make ice cream, homemade ice cream, and they use liquid nitrogen. So that would be right in here. That's 77. Liquid helium here. Dilution refrigerator, I'm not going to get into how that works. It uses liquid helium, but they can actually get into tens of millikelvin. Okay? And they have one on the University of Minnesota campus, which is why I specified in my provocative title that it's this campus. And then we start into 3 millikelvin. We start into the laser cooling regime, which is where we are. We're down here. Okay? Laser cooling, we're actually right in here. But laser cooling can get you all the way down in here. It depends on what atom you're working with. Okay? This corresponds to movement. I mean, what is temperature, after all? Temperature is a measurement, sort of a macroscopic measurement of speeds. Okay? You have a collection of atoms or molecules. The faster they're moving, the higher the speed, you assign a higher temperature to that. Okay? Whether it's vibration or just sort of zinging along in space. So anyways, this is tens of centimeters per second in this range that these atoms would be moving along. Okay? Now that's kind of significant because the molecules, nitrogen, oxygen, that are zipping around here that we're using very effectively, they're moving at hundreds of meters per second. Okay? So several football fields per second, the molecules and atoms in the room. And we can slow them down with laser cooling to a very small fraction of that, 10 centimeters per second. 10 centimeters is about like this. Okay? So, when we get down here, really funny things happen. You can actually use evaporation. I won't get into that too much. It's called Bose-Einstein condensation. But you can get down into the nanokelvin range, and really funny quantum physical things happen down here. These things are, these techniques and discoveries and demonstrations are important enough that in 1997, the Nobel Prize for Physics was given for laser cooling techniques, which is pretty recent on Nobel Prize scales. And then in 2001, another Nobel Prize was given for observation of Bose-Einstein condensation. And the idea is once you slow atoms down, you trap atoms, which is what I'll talk about, or you do this funny thing here, this evaporation, this condensation of these atoms, you can really get at fundamental properties of atoms in a way that you couldn't access before. So it's really a fun regime down there. So, factor of 100,000, let's count. So I'm going off the coldest place on campus is once a year at the chemistry ice cream party. Right? It's a lot colder than a cold day. Okay, so 1, 2, 3, 4, 5. This is where we sit. That's 5 orders of magnitude. That's 100,000. Okay, so I want to tell you a little bit about how laser cooling works. I have a lot of pictures in this talk, or several pictures and a movie, 2 movies actually, and very little scientific detail. I hope that's okay with you. If you're not satisfied with the level of scientific detail, I'm happy to have lunch with you if you pay. Okay, so this is how it works. Here's an atom that's coming with some velocity v. So this is sort of a time lapse A, B, C. This atom is zinging along with velocity v. This represents a photon, a little chunk of light, okay, from our laser. It's drawn with this sort of sinusoidal wave because it has a certain frequency or wavelength to it. and it propagates against the direction of this atom here. And if that laser is tuned just right, okay, atomic beam is bombarded by laser light. If that laser light is tuned just right, it will be absorbed by this atom. Okay? So atoms can absorb light, they can re-emit light. They generally will re-emit light. That's what's happening with this laser here. Okay? So this will, if it's tuned right, it will absorb. You can kind of see this is bigger than this. It's to indicate that the internal state of the atom has changed. Okay? It was like this and doing something, and now it's like this and doing something. Okay? So momentum, there's momentum associated with this. There's a momentum associated with this. This you probably understand, but this might be new. Momentum associated with this chunk of light. When this hits, it's like a collision, and this will get a little bit of a kick back this way because it absorbed it. All right? That's not a very stable system right now, so this wants to give up that extra energy that it has internally. So what it does is it gives it up to another photon. So it emits fluorescence out here. Now the direction of this is random. So it could come up this way, it could come up this way, it could come right back this way, it could come back this way. Okay. So the key to this this very simple laser cooling picture is after many of these photons, the direction of the re-emitted light is sort of cancels each other out. For every direction this way, there'll be a direction this way. But what doesn't cancel out is these two directions. This is coming this way, or this collection of atoms is coming this way. All the photons are going this way. So they all get this initial kick this direction. Okay? So after many, many cycles, this slows down because of this sort of light pressure and scattering. Remember, it's called scattering. Okay, so you might think that there's something going on here that I haven't mentioned. There's a few things going on here that I haven't mentioned. One is has to do with the Doppler shift. You're familiar with the Doppler shift? The train goes by, coming towards you, goes mee. That's not a train sound. That's a car sound. Car comes towards you, passes you. Okay, why is that? Because the sound that it's emitting from its engine, okay, sounds differently. I perceive that the frequency of that sound differently because the source is moving with respect to me. Same thing is happening here with light in this atom. Okay, this is moving this way, so in the atom's rest frame, in the atom's point of view, this is coming in from a moving source. Okay, so you have to worry about the Doppler shift in order for this to be on resonance with this. Okay, so I found a fun animation. That illustrates this. After a few absorption cycles, I slow it down, but then my laser light is now out of resonance because of the Doppler shift. So what this illustrates is the fact that I have to keep tuning. Oh, do you see that? Okay, so I'm going to try to aim at this atom. The atom's going to show me what its rest frame, I think the green means its rest frame frequency, but now it's not resonant anymore because I've slowed it down a little bit. The Doppler shift has changed, and now I have to change the color a little bit again. Okay, if I do that, if I'm conscientious about that, I can really start to move these things around. And I can even start to heat it up again effectively. There's scattering. See that? That bouncing off is that previous slide that I showed you. Okay? So this is just to illustrate that I have to worry about the Doppler shift. It's often called Doppler cooling, this effect. Okay, so this is one dimension that I showed you, but our results from the summer are trapping. Okay, so we have to worry about 3 dimensions. What I'm going to show you is an illustration of that. It's called actually optical molasses. And in this case, it's only 2 dimensions. But what I have here is a beam coming this way and a beam coming this way, laser beam. Okay? A beam coming this way and a beam coming this way, laser beam. Okay, so what I'm going to do again is I'm going to control the detuning of this laser. Okay, this is sort of at the target. But basically, I'm going to, just like I did in that previous animation, but now I have 4 beams. Okay, because I want to confine these things if I can. Let's see how my video game playing skills are. So right now, the atoms are just flying through the intersection region of this. Anybody can do that. Okay, so now I'm changing the color. I mean, it looks red, but I really am. Ah, did you see a little breaking of the atoms? So what's happening, what it's not explicitly showing in this case, is that scattering that you saw before. But that's the process that's slowing it down. Okay. Ooh, look at that. I got one. At that point, all these scattering effects are balancing from all the directions. Okay. Ooh, there's another one over there. Okay, so by changing the detuning, I'm not right on resonance with this, but so now I can actually go a little bit too far. Ooh, that's a nice target. This is what we did this summer. Now they're not actually still, right? There's still some small movement to these. The temperature isn't absolute zero, which means they're not completely still. Ooh, let's just watch this for 10 minutes. Now I can really mess things up by changing the frequency of my light or the color of my light much too far. Watch this. I don't know what's happening to those guys. They should be leaving. There they are. They need a little. They're actually being accelerated out. See the ones that fly in? They're actually being accelerated across that thing. And these will eventually go out of there. Maybe a problem in the simulation. So I have to get I guess the bottom line is I have to get the tuning just right, or the laser frequency just right. And that's what a lot of the work, student work in the lab is, working with the lasers to get it just right. Okay, so this is what we build. This is an artist picture of what we build here. And I put this up here for one reason, and that's to show you that lasers to trap the light. Lasers are not enough. You need these coils, or one technique is putting these coils in here that carry current in them, and that makes a magnetic field here. So these are the laser beams that I just showed you in that animation with the addition of the vertical. They take care of the other dimension. So there's a beam going in this way, the laser beam coming this way, the laser beam coming this way, and coming this way, down, and up. So there's 6 different laser beams doing what I just showed you in the previous slide. That will make molasses, syrup, but it won't trap them indefinitely, despite that animation. So we put this magnetic field on there. It carries a lot of current, 100 amps, and that's a lot of current. I think I'm going to sort of spin through this pretty fast. So this is the other scientific part that I'm going to show you. One of the triumphs of last century physics is the understanding of the atom, the internal workings of the atom. In particular, they developed this whole new system of math to deal with what's going on in this very small system. It's called quantum mechanics or quantum physics. Okay? And out of this came the understanding that an energy state in the atom is not continuous. It can't just take any energy state in this atom. There's discrete properties to these energy states. And every atom is different. Okay? They're all special in their own ways, these atoms. And there are a lot of them. And what I show you here is the specialness of lithium. Okay? So try to ignore the scientific notation here. Just focus on this line and this line. Okay? That is the difference in energy levels on a coarse scale that we have to use, we have to sort of target to do this laser cooling and trapping. It just so happens at 671 nanometers, which is in the red. So all our lasers are red in the lab because this is our target. If you look on a little bit closer scale, this is actually several lines that are separated. Okay? If you look on a little closer scale down here, it's actually 2 lines that are separated. Okay? This causes problems for us. Opportunities and problems. All problems are opportunities too, I guess. Saw that on the t-shirt. What happens is we end up needing 5 different colors. 1, 2, 3, 4, 5. I'll tell you a little bit more about these, but I don't think I will. But we need to be able to address all of these different transitions, and they're actually, because of this fine structure, which is called hyperfine structure, we need to do this. So it becomes kind of complicated to get 5 different laser frequencies, and they need to be stable. Okay, this is a quick test. What would happen if I have this one that says trapping on it, and I changed this? I had my laser, and it was fine, whatever this means. It was at the right place, right color. What happens if it accidentally sort of drifts off and gets, I don't know, up here? Based on the previous animations, what could happen? Start heating them up. Okay, so this has to be a stable length arrow, let's speak. Okay, so there's a lot of work involved in this. What I showed you here is the table on which the experiment sits. This in here is really the way that we generate all those 5 frequencies. Does it look like a mess to you? The students have a nickname for this. I can't remember what it is.
Forest.
The forest? I thought that was the dark forest. The dark forest. Okay, it's all dark color. Maybe also implying that it's easy to lose your way in here. But there's a lot of light. Anyway, okay, all of this in here generates that 5 frequency. So there's a lot of very careful alignment that needs to happen. This is really the main screwdriver in this experiment. Okay, this is a laser. It's the size of a shoebox. If you lift up that lid, you'll see a bunch of junk in there, but really at the heart of it is what's at the heart of this. Okay, this light here. It's a laser diode. Laser diodes are everywhere, right? They're cheap enough to be sold for a few dollars in the store. Okay. This one is not quite a few dollars, but it's not that much more. Okay, we have to do some things to stabilize that frequency, the length of that arrow. And then we use some tools over here to get derive those other frequencies from that laser. So this also has a nickname, LJ, Lauren Jr., because Lauren, who you'll see in the video that I'm about to show, spent a lot of time with this, as did several of the other students. So this is the forest that generates those 5 frequencies. Over here, I'll show you a close-up picture a little bit later. This is actually the chamber where those cold atoms sit. So this is a lot of fun to spend time staring into this. There's optics around it because you have to manipulate those light beams coming in all the directions that I showed you in that rendition. But a lot of student work has gone into this, and it's a lot of fun. I really, really enjoy it. And I think some students to some extent too. So I'm about to show you, there's some famous people in this video you might recognize. There are 3 students, Lauren Otto, who worked with us for a summer, 2 summers actually, and Dan, who's here, and Jack, both of them a couple of summers. So it's going to show Lauren in action with the forest and a high-quality interview. Let's see. Wait.
I've got my coffee cup, and I'm not afraid to use it.
They also put lithium in my coffee. Orange Dan, what's your favorite thing?
Oh, you know, just being here and showing up for stuff.
Yeah. What's your favorite thing about working in the Game Lab this summer?
Oh, the Te Amo Lab? My favorite thing is probably when we do the Soldier Boy dance. We've only done it once so far, but it was pretty good.
Those are the cold atoms. Okay, so I wanted to show you just a picture of the apparatus. So this is the other end of the table. This is the vacuum chamber. You might imagine with atoms that are so cold that are hanging out in there, you really don't want any of these 100 meter per second molecules whizzing by. Keep them in this trap. And so we put the entire thing happens in it's called ultra-high vacuum chamber. The pressure in here is less than 10 to the minus 7 torr. 10 to the minus 7 torr. Atmospheric pressure is over 700 torr. Okay, so I don't know, 11 orders of magnitude less pressure in here. There's almost nothing in there except for the lithium. That's what we're trying to get at here. So here are the windows through which these laser beams travel that I showed you. So in every case, you get a beam coming out this way and counter-propagating back, a beam coming in this way, counter-propagating back, a beam going down through the top and back up through the bottom, just like I've shown you to make. And here's the coils for the magnetic field, and when you look in there, that's when you see these cold atoms. Here's a quick stick figure of what I just showed you. This is looking down at the top of that ultra-high vacuum chamber. So it's like a stop sign chamber, ultra-high vacuum chamber. Here comes the laser beam from the forest, and you get this, what essentially amounts to counter-propagating beams in all three spatial dimensions. There's one going in and out of the page there. So how do we get the lithium? Well, it's this little cloud here. You buy it from the store, from a lithium store. This little chunk of metal that you stick in this. In our case, it's a brute force method. We stick it in this sort of tube, stainless steel tube, and then we heat it up to about 500 Celsius. Okay? We have to do that in order to get enough atoms to come into our region. Okay? It's a little bit ironic that we heat something so high to cool it down. But it's one of the challenges with lithium. This particular, it has a very low, what's called vapor pressure. So there's not much coming off of it unless you heat it up. So anyways, we heat it up, out comes spitting this atomic beam here, and that's where we get our lithium atoms. We also need to do something called lock the laser. Remember that arrow, that we can't let the length of that arrow change at all, otherwise we could start heating up the atoms. We have to have an absolute reference to do that. And this is where we derive our absolute reference. It's called spectroscopy here. We also have a laser beam that comes in and just like I showed you from the very beginning, counter-propagates the atoms that are coming this way to slow them down so they sort of drop into our trap here. Okay? So all these laser beams are going on in that apparatus that I just showed you. We can do some characterization once we have the atoms. Just don't even look at that part up there. Just look at this part here. Okay. When we look into the chamber, when we have the atoms, this is what we see. It's a glowing, very bright, in some cases, ball of atoms. And I remember when Dan sent me a text, I was off campus, and he said, I think we see cold atoms. And I was so excited. I can hardly do that anyways. I got back, and sure enough, I looked in the chamber. The whole lab is dark, right? There it was. So we can do some estimations. Dan did this particular estimation that they're based on the amount of light coming from that. Is it bright? Is it not so bright? Well, that corresponds to how many atoms are there. More atoms, brighter. So based on that and some electronics estimates, we have about 17 million of these atoms coming. So just another quick snippet of movie. You don't have to. Well, I was so excited I got out the really cheap Canon camera with the video and started taking the video. And what I want you to notice here is I blocked that slowing beam. I blocked one of the beams, and see how it fades away? That's a characteristic. That's a sure sign. That's what I wanted to do first. That's a sure sign that these are trapped atoms. Because they're so cold, they hang out there for a little while before they kind of fade off. Okay? So that fade off, when things are blocked, students took this nice data here What on the horizontal is seconds, time. On the vertical is fluorescence, how much light is coming off of these things. So you can see here, this is when those atoms are glowing red. There's atoms in the trap. We block the light beam, so there's no more trap, but the atoms hang out a little bit, and they slowly fade away. Okay? So how fast these fade away depends on certain things, like how good is the vacuum actually in there. And we can do the opposite. We can say, okay, let's block the laser beam, and then let's unblock it and let the trap go, and it takes a certain amount of time to build up to a steady state of atoms in this. So there's some cool physical information about the trap that we can get from this, but it's one of the first things we want to do for... So lastly, let me finish up with the next steps. Now that we have cold atoms, we could be the only undergraduate institution that has cold lithium atoms. There are several institutions that have cold rubidium atoms or cesium atoms. They're easier in some ways, in some key ways. But they're also in the near infrared. So you can't, when we look in the chamber and we see red, there's the cold atoms. When you look in the chamber of a rubidium trap, you see nothing, or just barely something, because the light is invisible to us. There are other ways to see it, of course, with a special detector and such, but one of the reasons we chose lithium is because we can see it. So anyways, my point is, I think we might be the only undergraduate institution with cold lithium atoms. So what do we do next? Well, recently I've been thinking about, we can do very precise spectroscopy of cold atoms, because some of the error associated with this Doppler shift implies motion, right? Motion of the train, motion of the car coming toward you. I had to deal with the motion in the laser cooling and trapping in the first place. But once we get them cold, they're just crawling along. That Doppler shift basically goes away. So that adds to your precision, it adds to your accuracy. So that's what we're after first. We want to do this cold atom spectroscopy with something called a frequency comb. I'll just quickly tell, I've been thinking a lot about frequency comb layers, frequency combs recently. This is my last slide. This person up here is Scott Diddams. He graduated from Bethel back in the late 80s, I believe, and now works at the National Institute of Standards and Technology. He's a wonderful scientist, wonderful guy. He's an amazing scientist, actually. And actually, Jessica, who I'm working with, worked with him this summer at NIST in Boulder. What he's showing you here is this really fancy laser, but coming out of that laser is, what does that look like? Rainbow? Something? It's a very broad spectrum. Put light into a prism, and you see something like that. Okay. Is that what you expect from a laser? Laser is really, you expect to get one color. In fact, my whole talk until now has been based on the fact that the laser is one color. We can control that color by precision. So what's going on here? Well, I'm not going to get into the tricks to do this, but the main method to get this broad spectrum from a laser is pulses. This is what that laser light looks like coming from that laser. There's no light, lots of light, no light, lots of light, no light. These are pulses. They're like pancakes of light. They travel very fast, speed of light. They last for only maybe 10 femtoseconds. Okay, that's 10 to the minus 15, 10 to the minus 14. So if you do a little bit of math on this, what this looks like in frequency and color is lots of teeth, very narrow teeth in frequency. So this, if you can build a laser that does this very, very nicely, what ends up happening is you get a very broad spectrum. But this broad spectrum acts like millions of little lasers, different colors. So what you have is you have a UV laser. There's not much power in a single tooth, but you have a UV laser. You have a green laser. You have a red laser. So you have all these lasers. So this means that we can do very precise and accurate spectroscopy of lots of different things. And that's what I want to do with lithium now, what we want to do. I haven't talked to Dan about it, but I'm going to say what we want to do. Recently, there's really only been two precision absolute frequency measurements spectroscopy of lithium. Okay, DAS and this work. This is taken from a paper, recent paper. So this work sits over here. Don't worry about what this means, but just concentrate on the fact that this work is the most recent one. This is the other precision measurement. They don't line up. In fact, here are some error bars. Usually you want your measurements to line up within the error bars. Okay? This is a problem. Lithium is important because it's a very simple atom. Okay? There are only 3 electrons associated with this. Okay? Which there's other elements that are much heavier and have lots of electrons. It makes it complicated. Lithium is so simple that you can make a measurement and you can make a very nice theoretical calculation and then ask about how they line up. And there's a lot of questions about this. Okay, so these were done, DOS and this work were done in an atomic beam. The atoms were flying along and they were doing their spectroscopy in the beam, like what I showed you in ours. But there hasn't been any cold atom spectroscopy, which could really help resolve some of these disagreements and give some new information. So I'd really like to try this. So thank you for being a cool audience.
So from a layman's perspective, why is this important? What could this lead to?
Well, really, that was the what I hope to get at with that last slide is new, very fundamental information. So this disagreement in experimental measurements also disagrees a little bit with the theory. So when you get a disagreement like that, you wonder, well, what's really going on in this atom? You start to question your knowledge of that atom. We thought we knew it, or we know it to some extent, but do we really know it? Is there something else going on? And the disagreements seem to say that there's something else going on there. So the application, or the cold atom spectroscopy with the cone, could really, somebody will do it. I'd like to do it here, the students. But that will probably really start to answer some of those fundamental questions about the atom itself. I'm not going to be able to commercialize this.
So is the trap in which you are able to capture these atoms, as it were, that's the magnet, is that right?
There's a magnet there. Yep.
Does that introduce heat into the equation? And do you measure that?
Yeah, that's a good question. There is heat generated from our magnet because it's an electromagnet.
Yeah.
It's not a permanent magnet. So we're running current through this like in loops, several loops, and that generates a magnetic field. And we can control, in that way we can control the strength of the magnetic field. But like I said, what you're probably thinking is there's a lot of current running through that, and 100 amps, you've got to have a big wire. And in fact, our wire is hollow, and we flow water through the wire to carry off the heat. It's pretty...
Can you measure the impact of the heat on the experiment or not?
Before we'd be able to measure it, we'd be in a situation where the wire would be melting, and it would be very unhappy. We'd all be sad. So we worry about other things. Yeah. Right now, because of that water that's flowing through the wire, we don't have to worry. Like, it doesn't affect the experiment. But
Thank you, Chad.